You know that feeling, right? You're staring at a national electrical code problem, and it feels like you're trying to solve a puzzle with a missing piece. Well, today, we're going to find that piece. We're talking about those mystery numbers that just pop into calculations out of nowhere. So let's crack this code.
You know the scene. You're deep in study mode, textbook open, calculator ready. You followed every single step, it's all making perfect sense, and then bam, a number shows up in the final calculation that was literally nowhere in the original question. Sound familiar?
And hey, this isn't just a hypothetical. This is a real question from a student named Abraham. He was working through an example in the 2023 NEC handbook and just hit this exact wall. It's a frustration we've pretty much all felt, and today we are going to get to the bottom of it.
All right, so let's dive right into the exact problem that tripped Abraham up. It's all about calculating the load for clothes dryers using NEC section 220.54. This is a super common scenario, especially when you're dealing with things like apartment buildings.
So here's the setup from the handbook. We've got 10 single-phase dryers, right? Each one is rated at 5,500 watts, and they're all connected as evenly as possible to a three-phase system. Our job is to figure out the minimum calculated load for the feeder conductors. Seems simple enough, doesn't it?
Okay, let's walk through how the book solves this. First, there's this kind of quirky rule for three-phase systems where we double the number of dryers on the phase with the most, which gives us 8 for the calculation. Next, we look at table 220.54, and it tells us to use a 60% demand factor for those 8 dryers. Now, a demand factor is basically just the code's way of saying, hey, it's super unlikely all these dryers will be running at full blast at the exact same time. We do the math, get our total load, and then we get to that final step. To find the amperage, all of a sudden, the number 208 volts just appears.
And that's it. That is the exact moment of confusion. We've been cruising along using the numbers the problem gave us, 10 dryers, 5,500 watts, and then this voltage that was never ever mentioned is suddenly the key to the entire answer. Now, this isn't a mistake. It's something else entirely.
The secret to cracking this code is this idea of an unstated assumption. You see, in a lot of these code calculations, some info is considered so standard for a particular situation that they don't even bother writing it down. The problem just assumes you already know it, based on the context.
So here's the deal. When you see a problem like this, with a bunch of dryers on a three-phase system, you're almost always talking about a multifamily dwelling, like an apartment complex. And the standard electrical service for those buildings is a 120, 208-volt, three-phase, four-wire system. It's just a more efficient way to get power to a whole bunch of units. That 208 volts, that's the phase-to-phase voltage, which is what these big dryers connect to. So the assumption wasn't stated, but it was baked right into the scenario.
Okay, so let's see if this whole idea holds up in another example. This next one's a little more complex. It's about cooking appliances from NEC 220.55, and you know what? It also shows why you should always trust your gut when something just doesn't look right.
Okay, so this time we've got a single branch circuit that's feeding 3 different cooking appliances. Let's say a cooktop and a couple of wall ovens. We just need to calculate the total load. Again, on the surface, seems pretty straightforward. So we follow the notes in table 220-55. We add up the ratings, get 21 kilowatts. Then there's a rule that says we increase a base load by 5% for every kilowatt over 12. Okay, that gives us a total calculated load of 11.6 kilowatts. But then, you got to look really close at that final step in the handbook's example. Whoa, hold on. We're dividing by 240 amperes? That makes no sense. The units don't even work. This is that moment where Abraham, our student, correctly thought, something is definitely off here. It looks like a typo, for sure, but it leads us right back to our main topic, unstated assumptions.
And yep, he was totally right. The handbook actually had 2 typos. The load should have been 11.6 kilovolt amps, not just volt amps. And the big one, the divisor should have been 240 volts, not amps. Abraham was right to question it. So, why 240 volts? Well, just like before, it's all about that unstated assumption based on context. We're talking about household cooking appliances. In a standard house or an individual apartment, the power for a big appliance like a range or an oven is going to come from a 120/240 volt single-phase 3-wire circuit. It's the most common setup there is. You get that 240 volts by connecting across the 2 main power lines.
Okay, so we've seen 2 different hidden voltages pop up, 208 and 240. Let's zoom out for a second and look at the single reason that ties both of these assumptions together. I mean, why does the code just expect us to know these numbers?
This right here is the absolute linchpin to the whole thing. Both of those sections we looked at, for the dryers and the cooking equipment, they apply specifically to dwelling units. That one little phrase is the most important piece of context you can have. These rules aren't for commercial kitchens or industrial laundromats. The code assumes that if you're doing calculations for dwelling units, you already know the standard voltages that are used in them.
And this table basically sums it all up. If you're working on a single-family home or you're inside an individual apartment wiring things up, you assume a 120-240-volt single-phase system. It's simple, it works, and it gives one unit all the power it needs. That's where the 240 volts for the cooking appliances came from. But if you're talking about the main service for a big apartment building that's feeding lots of units, it's way more efficient to use a 120-208-volt three-phase system. And that's where the 208 volts for that group of dryers came from. The context tells you the voltage.
So let's just boil all of this down into 3 crucial rules you can take with you for your next code calculation.
First up, context is king. You always have to ask, what kind of building am I dealing with? A dwelling unit has its own set of rules and, as we've seen, its own standard voltages. Number 2, know your default systems. If a problem doesn't give you a voltage, these are your safe bets for dwellings. And finally, and this one's a big one, question the source. If a calculation looks funky, it might just be. Your own practical knowledge is just as important as what's printed in the book.
See, when you start to understand these unstated assumptions, you're not just memorizing formulas anymore. You're actually learning to think the way the code thinks. The NEC is like a language, and by understanding its context, you're getting one step closer to being fluent. Now you've got the tools to start finding those missing puzzle pieces for yourself.